In this short video, we are going to discuss about the addition of 16-bit in 8086 architecture using a NASM assembler and GDB as the debugger. Okay, so you can see on the screen the code has been written in the left side and the steps to execute is shown in the right side. Okay, so when we start to the coding, we are simply taking the two numbers of 16-bit mechanism. So one number will be received AX register, AX one. A second number we are going to receive in BX register. Again, I am taking the same number 1, 2, 3, 4. So these numbers are actually considered to be as a 16-bit number, and AX and BX are the 16-bit registers. So the result after adding these numbers AX and BX, the result will be in AX, which is also a 16-bit. And now we want to show the result on the console. Before showing it on the console, we sum, which is of the size of data of word size. So using the pointer to sum, we are going to just shift the value from x to sum, and now we want to see the result. Showcase the result, we are using the system right call. So move ex comma 4, ebx 1, and move ec comma sum. Take the result into that ec register, and the size is of bytes, and finally the int ATH will be the kernel call. So if I want to show the out, if I execute this code, it will show the some symbolic representation of the ASCII value. Okay, but actually we need to see the result, how the hex value is going to generate, or how the addition will be happening inside the AX register. Result will be in the AX register. How to do that? For that purpose, we need to go with the additional steps, which are nothing but debugging steps. So let's start the coding. So first, write your code. So I'm using the gedit as a editor. Give the file name add16.asm. The code is written into the file already. So I'm going to save this code and close the file. Now we want to go for the second step, that is assembling. So NASM assembler -F to generate the O files, -G to generate the debug symbol files, -L to generate the list file with the name of add16.lst, and with whom I want to generate. This is my assembly code. Okay, just enter. Sorry, just 1 minute. I forgot one step. -F, and I'm going to use the ELF command. Okay, enter. Yes. So it has generated the .o file, .lst file, and the debugging symbolic file. Okay. So once these three files has been generated, now it's time to load and create the executable. I'm writing the step for that. ld -m ELF in the format of i386 debugging mechanism. Add 16.o is my object file generated. I need to give the name of the same, add 16. So you can give any other name, but I'm going to continue the same name as the assembly file name has been given. So click on OK. So once I click on enter, it will generate the executable file. So if I want to see the output of these two files, the 1234 in decimal plus 1234 in decimal, the result will be a 2468 in decimal, but that value will be actually going to represent in the form of ASCII. So /add 16. If I give this command, it's showing some representation with question mark and some symbolic representation. So I'm not able to understand whether addition has been done or not. So for the purpose, we are going to use the concept debugger. Now type the command GDB, name of the executable, add 16, enter. So already debugging symbolic file has been generated, so it has been loaded into over here. The next step is to align the breakpoint. Where to break? At the start of the code. Now initiate the run of that file. We are going to run that code with the respective breakpoint. So we are just giving a first breakpoint and then we are going to run it step by step. Okay, so once the breakpoint has been done, now it's time to set the assembly flavor to the Intel platform. Set this assembly flavor to Intel. Okay, and now as we are interested to see the output will be in the form of registers. So set the layout for the assembly and layout for the register. So this is the layout for the registers section, and now it's time to check the code one by one. So we are right now at the first part, underscore start. So if I type here as a next instruction, so it will execute the move ax comma 1 2 3 4. So at right now in ax the value is 0. So if I click on this first line, the value in eax, you can see now it's 0x4d2. It's an hexadecimal and its decimal format is. So if I again click on next I, now bx will be loaded by 1 2 3 4. You can see ebx will be loaded by 1 2 3 4, and now the third instruction is nothing but addition of ax comma bx. If I click on that next instruction, that is third instruction, add ax comma bx, you can see the result in eax, that is 2468. Okay, so in this way just we have executed the code to understand the actual addition of the two values, and the result will be in the eax. So now if I again click on the next value, next I, so actually in next I the ax will be stored to the sum as a pointer. So sum is the one of the address of the variable in the dot data section. Now the value from that will be stored to the particular address. Okay, so just we have dumped that value to an, and now in next line move ex comma 4. So now it's time to run the code for the displaying output on the console. So if I click on next I, so 4 will be loaded into ex. So step by step, if we go further, the values are going to load into the system and it is going to take the output. So just you can see in ex he has been received one value from the pointer, and now edx size is equal to 2 bytes, and at the last we are going to execute the execution code for the int ath. Okay, so in this way step by step we have just executed the code and seen the output. Okay, so this is how we can go for the actual execution of the code. So if you have the mechanism to understand how the addition is happening in the registers, you can go through the GDB mechanism. In the next video we can see how the actual output has to see to a particular memory address. Okay, thank you so much.